Good morning, welcome to this lecture 4. So today we will discuss exponential and logarithm functions. So logarithm and exponential functions. So naturally, we will start with the logarithm. And we will focus essentially in the natural logarithm. So the natural logarithm is a function that we denote by f of x equals ln of x. So what is this function? So there are several ways to approach that, but I will introduce this function with a theorem. So we discussed the two last lectures was about derivatives, and thanks to that, I can now introduce the natural logarithm as follows. So theorem, there exists a unique derivable function f, so defined on the interval of positive numbers such that two things. First, f prime of x equals 1 divided by x. And furthermore, f of 1 equals 0. Okay. So there exists, so we can prove that there exists a unique function such that when I take the derivative of f, I obtain 1 divided by x, and furthermore, for x equals 1, f of 1 equals 0. So this function is, so it's the natural logarithm, so it's called natural logarithm or just logarithm, and it is denoted by f of x equals ln of x. Right? And so this function has some properties. So so the logarithm is only defined for positive numbers. So if I pick up two positive numbers, a and b, then I have that the logarithm of a times b equals ln of a plus ln of b. Also, ln of a divided by b equals ln of a minus ln of b. So this says that the logarithm transforms the product into sum. And as I said the last time, that's how it was introduced by John Napier, they say, introduced by John Napier in the early 17th century. So just a quick remark. There are other logarithms, and we write it log b. So this is a logarithm with a basis b, but you can define those logarithms as with the following expression. So you will say that is 1 divided by ln of b times ln of x. So those logarithms are defined through multiplication of the natural logarithm. Okay. So we will see later another property of the logarithm. Okay. So now let's deal with the graph of the logarithm and the limits. So first, the limit when x goes to infinity of ln of x. So now I will speak about the natural logarithm. So when x goes to plus infinity, then ln of x, ln of x goes also to plus infinity. And so the logarithm is defined for positive numbers, but when x goes to 0 plus, then the logarithm goes to minus infinity. Also, we have that ln of x prime is 1 divided by x. So this is a positive number. And you know that if on a given interval, the derivative is positive, this implies that the function ln is increasing. Okay. So in fact, I can sketch the graph of the logarithm function here at the x-axis, and on the y-axis, I will put log of x, and so let's do it another way. So if I draw the function ln of x. So for x equal 1, it's 0, and it goes like that. So it always increases, but so since the derivative is 1 divided by x, you know, as x becomes bigger and bigger, the derivative becomes smaller and smaller, so that the growth becomes smaller and smaller. But that's the sketch of the graph of the function ln of x. All right, so this is the essential of the logarithm. Now let's move to the exponential function. So there's several ways, again, to define the exponential function. Here, I choose to define it as follows. So we look for a function such that when I apply f to ln of x, I get x. So a geometrical way to see it is, so let's draw here our log function. So a way to see that is just to make a transformation of that. I will flip this, and I will flip this. And if you want, I look here, and I want that the image of here, of this value, I want it to be exactly x. So I want that the image of the ln of x, I want to be x. So I just have to look at here. If you consider this to be x, and here, and you look that, so I flip this. If I flip that, I obtain exactly this function. So this is just to give you an idea. So yes, so the question is, can this function exist? Yes, it exists. It exists. It's also equal to log of f of x. And so such a function exists, and it's unique. So we call it the exponential function, and we write it as f of x equals exponential of x. All right, so now So I introduced the logarithm thanks to its derivative. Now I introduce the exponential as the inverse function of the logarithm. So this, when I have this property for a function, then the function f is called the inverse of here the function logarithm. So, but let's look at now the derivative of the function exponential. And so to do that, we can actually compute the derivative thanks to the chain rule for derivatives. So I know that, so for my function exponential, I have that the logarithm of f of x equals x. So I will take the derivative on both sides. So the derivative of x is 1. And the derivative of ln of f of x, thanks to the chain rule, I recall the chain rule, for example, here, the derivative of g of f of x is g prime at f of x times f prime of x. So if I apply that here, I obtain that, so the derivative of the ln is 1 divided by, so it's 1 divided by f of x times f prime of x equals 1. So I see here that f prime of x equals f of x. So that's a very interesting property of the exponential. That is, when I take the derivative of the exponential, this is nothing but itself. This is a very important property of the exponential. Also, so I have y, let's say y equals log of x, then applying the exponential, I have exponential of y equals x. So I know that ln of 1 is 0. So applying that, I have that 0 equals ln of 1. So if I apply exponential here, I got exponential of 0 equals 1. And finally, we know, let's say that when x goes to plus infinity, so this is plus infinity, and so the exponential is defined on R, and as x goes to minus infinity, this is 0. But the exponential is always positive, and I can summarize with the graph of the exponential like that. So at 0 it's 1, and so you know the derivative of exponential of x is exponential of x. So the derivative is itself increasing, and it's becoming bigger and bigger. Okay, what are some properties of the exponential? I will just write by symmetry with the logarithm. So we now have that exponential of a plus b equals exponential of a times exponential of b, and exponential of I minus B equals exponential of A divided by exponential of A. All right. Again, by symmetry with the logarithm, I can, in fact, define exponents. So you know that for let's say so you know, for example, 3 to the power 7 equals 3 times 3, 7 times. But now I can define B. So for a positive number B, all positive number, not just integers, and any x, I can define this quantity as exponential of x ln of b. And so you have that ln of exponential of x equals x. And if I look at log b of x, so this is 1 divided by ln of b times ln of exponential x ln of b. So I made, no, sorry about that. So yeah, so sorry, I didn't want to write log b of x, but I wanted to write log of b to the x. So log of b to the power x is by definition 1 divided by log of b times log of times ln of b of x, but ln of b of x is that, so it's x ln of b, but ln of the exponential of a number is just the number itself. So here you can obtain here that this is just x, right? So in the same way that the ln of e of x is x, also the log in base b of the exponential of with basis b of x is x, right? So I don't want to insist much on that. I just wanted to focus on the natural exponential and the natural logarithm, but you have also you can now define the power or the exponentiation for all numbers b, and also you have other logarithms with other bases. All right. So we will continue the discussion of the exponential. So I have to say that exponential and logarithm are widely used in various science applications, biology, physics, and even in mathematics. Logarithm and exponential are everywhere. So in lot of topics in math, logarithm and exponential appear. So one of the basic yet very important examples is what we call differential equations. So differential equations are also very used in applications because they describe the evolution of some quantities across time. So they are also widely used in science. And now, if I consider, let's say now I look for a function such that when I take the derivative, I obtain a times itself. So with this, just this point, it makes you think about exponential, because you know that the exponential satisfies this equation with a equals 1. And let's say we look for a function, define, let's say, over all the numbers, and let's assume that so usually in applications, a lot of applications deal with the variable is the time. So I will use this term. Let's assume that at time 0, you have the value k. And let's look at this function y of t equals exponential of at. So if I took the derivative, what do I obtain? I obtain y prime of t equals, so again, the chain rule for derivative. So my variable is t, I obtain a, because it's the derivative here, and the derivative of exponential is itself. So I obtain that. So, but this is y, so this is a times y of t. So the function y of t is a solution of that. And if I look at the value of at 0 of this function, so I just forgot the k here. So if I put a k in front, I will get a k in front. This is still valid, but now at time 0, because exponential of 0 is 1, I got k. So the solution of this equation is this function. So it's an exponential. So yeah, that's an important use of exponentials. They satisfy this differential equations. All right, so we could practice now for the derivatives by using exponential and logarithms. I will just end this lecture by giving you a glimpse of other possible definitions of exponential of x. You can also define exponential of x as a limit. This is the limit as n goes to infinity of 1 plus x2 divided by 2 plus x to the third divided by 3 factorial 3 plus all the way up till n. So we can write that also with this notation. This is the sum from k equals 0 to n of xk divided by k factorial. Okay, and yeah, this is also equal to exponential of x. And this is for all x in R. Another, so this relates also to the work of Euler in the early 18th century. So, and you have also that exponential of x is also the limit as n goes to infinity of 1 plus x divided by n to the power n. All right. Okay, so I hope this short discussion about exponential and logarithms is useful. Of course, you could say much more things, and you could do a lot of exercise, but you can now this is a good introduction, and then you can dig into those concepts with other sources. All right, thank you very much, and bye-bye.